Welcome to lecture series. We have seen if V and W be two vector spaces of dimension say n and m respectively over the field capital F, then the collection of all linear transformations from V to W is a vector space. We also seen that when V equal to W, that it basically collection of linear operators from V to V or linear operator on V. Today we want to answer the following questions. First question is it possible to represent a linear transformation by a matrix? In general, the answer is no. It depends on the vector spaces over which linear transform is defined. If the linear transform is defined over the finite dimensional vector spaces, then it can be represented by a matrix, please. Next question will be whether this matrix representations, is it unique? If at all it is possible to represent linear transformation by a matrix, then is it unique? Is it unique? Again, answer will be it depends on the given order basis. So, for a given order basis, it will be unique. The next will be how to find the matrix representation of a linear transformation which is defined on finite dimensional vector spaces. Yes. So, consider V and W be two finite dimensional vector spaces over a field say capital F with dimension n and m respectively. Let B equal to alpha 1, alpha 2, alpha n and B prime equal to beta 1, beta 2, beta m be the order basis for V and W respectively. So, I have considered they are the order basis. Now, this order basis now are fixed, please. Okay. Let T be a linear transformations. So, from V into W, please, V into W, that is T is mapped from V to W. Fine. We want to find out a M cross N matrix, which will basically will say that matrix representation of T related to order basis B and B prime. This one's okay. So, for this what I will do, consider alpha belongs to V, be any element. Since alpha belongs to V, I will be able to express alpha in terms of the basis element of V. So, there exist n scalars x1, x2, xn belongs to capital F such that alpha equal to sigma j equal to 1 to n. That is coordinate matrix of alpha with respect to order basis B equal to, if I write, is a capital X, which is equal to x1, x2, the coordinate xn transpose. Since T is a linear transform from V to W, now for each alpha j belongs to V, I will be able to express the image of alpha j under T by the basis element of W. I mean to say, for each alpha j belongs to V, the T alpha j can be written as linear combinations of beta 1, beta 2, beta m. I mean to say, there exist m scalars A I j I equal to 1 to m. So, I can write down the T alpha j like this. Of course, the linear transformation T will be defined by the action of T on each alpha j basically. So, from this also one can define the linear transform T, please. Now, what can you say about the image of alpha under T? So, image of alpha under T, that is T alpha equal to T of sigma x j alpha j, j equal to 1 to n, this is equal to sigma x j T of alpha j, j equal to 1 to n. If I consider this is equal to star, then using star, so this is equal to, I can write down sigma x j, j equal to 1 to n is T alpha j, again sigma a I j. So, a I j I equal to 1 to m and beta I. Okay. And this is a finite sum. So, I can extend the order of the sums. So, I can write down this is equal to, again sigma I equal to 1 to m and sigma your a I j x j this whole multiplying to beta I. So, this implies the coordinate of T alpha with respect to B prime order basis having rth entry as rth row of Ax, that is, if I write A11 x1 plus A12 x2 plus A1n xn and your AM1 x1 plus AM2 x2 xn, if I write like this is my Ax. So, Ax equal to this quantity. Okay. Now, this is a column. So, this column rth entry is basically AR1 x1 plus AR2 x2 plus ARn xn. So, the rth row of Ax is basically the rth entry of the coordinate of T alpha with respect to B prime. So, this implies the coordinate matrix of T alpha with respect to B prime, which is transpose of that one. So, this is basically, if I consider this equal to C1, C2, see that C1 is equal to this sum, C2 is equal to second row and like that, then this is equal to transpose of this is equal to Ax. Here this is again A into x, means x is what? X is the coordinate matrix of alpha with respect to order basis B. So, this is, I can write this is equal to like this. Here A is M cross n matrix over F and is known as matrix representation of T relative to order basis B and B prime. Symbolically, I can write down equal to A. Now, certainly you may expect that if I change the order basis, then what will happen? If I change the order basis, I will get another matrix place, another matrix representation place. But if I fix order basis, then I am getting unique, this will be unique matrix place. Here the A equal to first column A1, A2 and AN, if I write this is the A matrix where A1, A2, A3 and AN denote the first, second and nth column of the matrix A, then T alpha j, coordinate matrix of T alpha j with respect to B prime equal to Aj, because T alpha j in star is equal to sigma Aij beta I. This is basically saying your jth column of the matrix A, where A is equal to Aij, please. So, what we have obtained for a given linear transformation, I have obtained an M cross N matrix, please. Now, if an M cross N matrix Q is given over say capital F, then is it possible to have a linear transformation from V into W? Answer is yes. How? It is like this. I can define say u of alpha, which is equal to u of sigma xj alpha j, j equal to 1 to n, this one. This is equal to, I can define like this, I equal to 1 to m and j equal to 1 to n. If I say that q is equal to small q I j type, okay, so I can say q I j and x j then beta I, where q equal to q I j. So, this is m cross n matrix space. Then I am getting this type of expressions. Now, this u, the way I have defined it here, it is a linear transformation. We can immediately check capital U is a linear transformation from V into W. So, what we have seen, there is a one-to-one relation between the set of linear transformation from V to W, that is from LVW, to set of all m cross n matrices over the field capital F. So, let me write down in formal way. So, what is the conclusion here? So, I can write like this. Let V and W be two finite dimensional vector spaces over a field capital F with dimension n and m respectively. Let B and B prime be order bases of V and W respectively. Then for each linear transformations T from V to W, there exists a unique m cross n matrix A over F such that for each alpha belongs to V, coordinate matrix of T alpha with respect to B prime equal to A into coordinate matrix of alpha with respect to B. Furthermore, for T to A, for each linear transformation there exists a m cross n matrix from T to A, this mapping is 1 1, is 1 1. I mean to say, if I consider m cross n matrix over the field capital F, then also one can find out a linear transformation from V to W. That is, if capital S denote set of all m cross n matrices over F, then there is a one-to-one relation between LVW and capital S. So, that is what we have proved, please. Now, let me consider some examples. Consider a linear transformation T from F3 to F2. I mean set of all 3 tuple space to 2 tuple space defined by T of x1, x2, x3 equal to, let me consider x1 minus 2x2 comma x2 plus x3. Suppose I have taken like this randomly. So, we can check this is a linear transformation from F3 to F2. Okay. Consider B equal to E1 equal to say 1 0 0, E2 equal to 0 1 0, E3 equal to 0 0 1. This is a standard order basis on F3 with space of 3 tuples, and B prime is equal to, let me consider see E1 prime which is equal to 1 0 and E2 prime say 0 1, some name. We can also give alpha 1, alpha 2, alpha 3 instead of E1, E2, E3, and then beta 1, beta 2, E1 prime and E2 prime also. Then what is the matrix representation of T related to order basis B and B prime? First we have to know this one, please. To find that one, what I have to do? According to the definition, we have to see the image of E1, E2, E3 under T also. First, T of E1, T of E1 is equal to 1 comma 0, because x1 minus 2x2 comma x2 plus x3. So, T1 E1 goes to 1 comma 0. Now, this I have to write down in terms of C1 and your E1 prime plus C2 into E2 prime. So, this is equal to C1 into 1 comma 0 plus C2 into 0 comma 1. So, this implies that C1 equal to 1 and C2 equal to 0. We can immediately check it, this one. Okay. So, if I denote the matrix representation of T related to order basis B and B prime is equal to say capital A, then the first column will be 1 0. Now, to find the second column, I have to see again the image of T2. T2 is equal to, it will be minus 2 and plus 1. This is equal to say again some C1 into 1 comma 0 plus C2 into 0 comma 1, this is equal to C1 comma C2. So, this implies C1 equal to minus 2 and C2 is equal to plus 1. So, the second column will be minus 2 and plus 1. Then T3, image of T3 will give me third column. T3 is equal to 0 and 1. So, this is equal to, I can write down 0 into E1 plus 1 into E2 prime. So, this implies the third column will be 0 and 1. So, the matrix representation of this linear transformation from F3 to F2 is given like this, A equal to this quantity, please. Let me take another examples. Okay. Here one more thing let me tell you. Now, instead of this standard order basis, if you take any other order basis, then you can also find out the matrix representation of corresponding to that order basis, please. This B I will replace by, say, my alpha 1 equal to 1 1 1, alpha 2 equal to 1 1 0, alpha 3 equal to 1 0 0, and B prime I will keep it as it is. Then also you will have a new matrix, please. The matrix representation, suppose in that order basis you start B star and then other one is B prime, then matrix representation of T related to B star and B prime will be different, please. You may again cross check, is it possible to correlate the two matrices again? Please take it as a homework and see it, please. We will come to these questions maybe the next class, please. Okay, let me take another examples. Let V be the space of all polynomial function of degree less than equal to 3 over the field is capital F. So, this vector space is also finite dimensional of dimension 4, please. So, consider basis as 1 x, x square and x cube. Let me consider W also equal to V and B prime equal to also B. So, let T be a linear transformation from V into V, that is here T is a linear operator, please. For any P belongs to V, P will be of the form P naught plus P1 x plus P2 x square plus P3 x cube, something like this, because polynomial of degree less than equal to 3. So, like that, please. So, let me define T of P, this is equal to P1 plus 2 P2 x plus 3 P3 x square. So, basically the T I have considered it is a differential operator, please. Now, what can you say about the matrix representation of T? I can say like this, equal to what? This is the question, please. Now, I can again we can proceed by earlier method. Here we have basis functions as 1 x, x square and x cube. So, now I have to see what is the image of T of 1. T of 1 will be equal to what? So, this is the definition. If I use this definition, T of 1 equal to 0. So, now I have to express 0 the linear combination of 1 x, x square and x cube. So, this is equal to C1 into 1 plus C2 into x plus C3 into x square plus C4 into x cube. So, this implies that C1 equal to C2 equal to C3 equal to 0. Okay, this is equal to like this thing. So, suppose this is equal to matrix say capital A, then the first column will be 0, 0, 0, 0. What about T x? T x equal to 1. So, this means that second column will be, so second column will be, this is equal to 1 into 1 plus 0 into x plus 0 into x square plus 0 into x cube. So, this will be 1, 0, 0, 0. Similarly, T of x square will be 2x. So, this will be again 0, 2, 0, 0, and third T x cube will be 3x square. So, when you express in terms of this basis element, then the coefficient will be 0, 0, 3 and 0. So, the corresponding matrix representation of this operator will be this matrix, please. Now, we are curious to know, if I consider S as a set of all the m cross n matrix over the field capital F, and this is one set and another one is LVW, where V having dimension n and W having dimension m. Is it possible to have an isomorphism relation between these two sets? Let capital S denote set of all m cross n matrices over F. Then claim there exists an 1-1 linear transformation from LVW into S. 1-1 we have already checked, only we have to check that if I consider psi is a function from LVW to S, which is basically saying that any transformation goes to corresponding matrix representation of T related to the order basis B and B prime. Okay. Fixing order basis P and B prime of V and W respectively. So, this is fixed, please. Now, is it possible to have a function from LVW to S which will be 1-1 and linear transformations? So, this we can answer if I somehow show that if T1 and T2 are two linear transformations belonging LVW, and if the matrix representation of T1 is a capital A and matrix representation of T2 of course related to this fixed order basis is a capital B, then matrix representation of any constant C times T1 plus T2 equal to C times A plus B, please. If I somehow can show this one, then this question is answered, please, because anyhow we have shown that the function mapping T to the corresponding matrix representations, this is a 1-1 mapping, place, we have seen it. Now, just we have to check that it is a linear transformations. So, if T1 and T2 are any two linear transformation from V into W, let B and B prime be the order basis of V and W respectively. Let dimension of V and W be N and M respectively, let the matrix representation of T1 is equal to capital A, which is M cross N matrix, M cross N matrix over F, and matrix representation of T2 with respect to B and B prime is equal to say B, which is equal to say Bij, again this one. Then any constant C times T1 plus T2, if I consider this one, the matrix representation of C times T1 plus T2 related to order basis B and B prime will be C into A plus B. This is a claim, please. We know T1 of, okay, let me just consider basis, please. Okay, consider B equal to alpha 1, alpha 2 and alpha n, and B prime equal to say beta 1, beta 2 and beta m. So, this is my order basis V and W respectively. Okay. Now, we know T1 of alpha j, coordinate matrix of T1 of alpha j with respect to B prime equal to, that is Aj. So, and coordinate matrix T2 alpha j with respect to B prime is equal to jth column of the B matrix, that is given to us. Now, so C times T1 plus T2, this will be again linear transformation from V into W, and when this one acting on alpha j, which is equal to C of T1 alpha j plus T2 alpha j. So, this is equal to C times T1 alpha j is equal to, according to this given condition, this is Aij I equal to 1 to m, and this will be beta I plus T2 alpha j will be again, this will be sigma Bij I equal to 1 to m and beta I, please. So, this is equal to sigma C times Aij plus Bij times beta I equal to 1 to m. Okay. So, this implies that coordinate matrix of Ct1 plus T2 when it operating on alpha j with respect to order basis B prime will be equal to C times this your jth column of the A matrix plus jth column of the B matrix, please, this one. So, this implies the matrix representation of Ct1 plus T2 related to B and B prime will be C times A plus B, please. So, what we have learned? We have seen that there is a one-to-one correspondence between the set LVW to this set of all M cross N matrix capital S, and this one-to-one function, that psi, this will be also a linear transformations. I mean psi of Ct1 plus T2 will be equal to C times psi of T1 plus psi of T2, that is equal to Ca plus B, please. So, what we have learned? So, today we have learned that First is that there is a 1-1-on-2 mapping, not only 1-1-on-2, it is a linear mapping between the set of all m cross n matrices and set of all linear transformation from V into W, when dimension of V and dimension of W is n and m respectively. So, that is the very interesting results. So, this will give an opportunity in our next all lectures that instead of talking linear transformation, one can also deal with the corresponding matrices also. Thank you.